Hello everybody, my name is Yehonatan Fridman and this is our collaborative work under the supervision of Dr. Oren and Professor Hagit Attiya from the Technion and Professor Danny Hendler from Ben-Gurion University. Today I would like to talk about our exciting introduction of non-volatile RAM into the real supercomputing world. So obviously HPC is evolving and growing into larger supercomputers that fill the growing needs of scientific research and advanced industries. Because supercomputers become more and more complex and with many compute nodes and components, they tend to experience frequent faults. This issue becomes highly relevant when we go to exascale. Predictions say that exascale systems will probably experience crashes every few hours or even few minutes. This is a critical issue for long-term computations. So what can we do about it? In this work, we investigate how non-volatile RAM, which is called NVRAM, can be used to increase the fault tolerance of iterative solvers. Fortunately, modern designs of supercomputers will integrate NVRAM. For example, the Aurora supercomputer will consist of Optane DCPMM. NVRAM provides persistency, large capacity, it is byte addressable, perfectly fits the gap between DRAM and storage, and as such could perfectly fit. Let's investigate how. In the last decade, exact state reconstruction techniques, ESR for short, were investigated to support the recovery of linear algebra iterative solvers by avoiding checkpointing the entire computation state. The main solver we focus on in this work is the prevalent preconditioned conjugate gradient. In the ESR method, variables that cannot be reconstructed from failures create redundancies on other compute nodes RAM. In the CG method, this is the variable P. The idea is that some values of P are already transferred between processes, so in some way redundancy is created naturally. When failure occurs on some processes, redundancies of their data are collected from other surviving processes on a spare reconstruction node. The other state variables are reconstructed by calculations, and then the computation of the solver continues. However, ESR has many limitations. To support recovery from multiple node failures, many copies of a variable have to be created on multiple nodes. This creates a huge memory overhead on RAM. Moreover, redundancies are passed to other processes via message passing interface, so ESR also suffers from networking and time overheads. ESR in general does not support NVRAM and its persistency, which is a main disadvantage for the next supercomputers. In our work, we adjust ESR to support NVRAM. In this model, which we name NVM-ESR, the ESR variables that used to create redundancies on RAM are now persisted only once to the NVRAM on each persistence iteration. To address this model in reality, we consider and support two cluster architectures. The first is the homogeneous NVRAM cluster, in which each compute node is equipped with its own local NVRAM. In each persistence iteration, data is transferred to the NVRAM via local persistence operations with PMDK libraries or with the local MPI windows over the NVRAM. Note that when a node fails, we need to wait for its recovery before the NVRAM can be accessed again to read the recovery data and to continue the computation. The second architecture is the remote persistent recovery data subcluster, in which NVRAM exists on the remote subcluster and not on the compute nodes themselves. Persistent operations are achieved by RDMA operations over one-sided MPI communication to the NVRAM. This architecture is more representative of the design of the next supercomputers. In this architecture, when a compute node fails, data can still be accessed from the remote NVRAM by another spare node. We evaluate NVM-ESR and see that RAM usage is significantly reduced compared to the traditional ESR. In both architectures, NVM-ESR is much more efficient in time overhead than ESR. As expected, time overheads of the remote NVRAM subcluster are higher than that of the homogeneous NVRAM cluster due to network overheads of remote operations. We demonstrate that NVM-ESR can save enormous RAM space on the Aurora supercomputer, enabling it to run much larger problems. To the best of our knowledge, our work is the first to report on a scientific application implementation that accesses remote NVRAM in this manner for recoverability. We conclude that NVM-ESR significantly reduces time and memory overhead of ESR, providing efficient recovery models to linear algebra solvers. Thank you.